Extreme heat is one of the most critical and recurring challenges faced by cities in the United Arab Emirates. During summer months, temperatures frequently exceed 45 degrees Celsius, causing electricity demand to spike sharply. The primary reason for this surge is air conditioning, which becomes essential for daily life, public safety, and productivity. This places significant stress on the power grid, increasing carbon emissions and reducing the overall resilience of urban energy systems. A major and often overlooked issue is how inefficiently electricity is used within existing urban infrastructure.
A major contributor to this inefficiency is conventional streetlights. Streetlights operate every night at full brightness, regardless of traffic density, pedestrian movement, or lighting conditions. Even when the roads are empty, the lights are completely on. In a city like Dubai, with thousands of streetlights operate simultaneously, this creates a constant and unnecessary electrical load, exactly when the grid is already under stress due to cooling demand. Now this raises an important engineering question. Can existing city infrastructure be redesigned in such a way to reduce energy waste and support cities during extreme heat?
Why streetlights? We chose streetlights deliberately. Streetlights are already deployed at a massive scale and they are government-owned and centrally managed. They are structurally ideal for mounting solar panels, sensors and electronics, and they are directly connected to the city's energy network. Yet today, they are passive electricity consumers. They do not think, adapt or respond to real-world conditions. Our idea is simple but powerful. Transform streetlights from passive loads into intelligent systems that actively support cities during extreme heat.
Streetlight integrates a compact solar panel mounted at the top of the pole. The panel has dimensions of 0.66 meters by 0.4 meters, giving an area of 0.264 square meters. Assuming 20% panel efficiency and average UAE solar conditions of 5.5 peak sun hours per day, the daily energy generated is approximately 0.25 kilowatt hours per day. This energy is generated during daylight hours when streetlights consume almost no power.
To complement solar energy, each streetlight also integrates a vertical axis wind turbine designed specifically for urban environments. Unlike traditional turbines, vertical axis turbines can operate under low, turbulent, and multi-directional airflow, making them suitable for roadside conditions. The turbine uses a helical blade geometry, which enables smooth rotation, reduced vibration, and low noise. Although ambient wind speeds may be low, passing vehicles generate repeated airflow disturbances. Using a conservative effective wind speed, the turbine produces approximately 0.08 kilowatt hours per day.
Light uses a realistic sensor set, nothing excessive, nothing impractical. A motion or a presence sensor similar to those used in automatic doors and smart lighting systems is mounted just below the lamp head, approximately 3 or 4 centimeters above the ground and angled slightly downwards. This allows it to detect pedestrians, cyclists and vehicles over a radius of 8 to 12 meters, covering both the sidewalk and the roadway. An ambient light sensor no longer than a few millimeters is placed on the top or the side of the lamp head. It faces the sky and is positioned so it is not affected by the lamp's own light, allowing accurate detection of daylight and dusk conditions.
A temperature sensor, roughly the size of a matchstick head, is mounted mid-pole inside a ventilated casing on the shaded side of the streetlight. This prevents direct solar heating and also ensures that it measures true ambient air temperature, not just surface heat. Optionally, a small internal rotation sensor is placed inside the wind turbine housing to monitor turbine activity. This sensor is fully enclosed, protected from dust and rain, and has no visual impact. All sensors are compact, low cost, and are already widely used in existing urban systems.
Data from these sensors is processed by an AI-driven energy management layer. Rather than reacting in real time, the system becomes predictive. It analyzes traffic patterns, temperature trends, lighting demands, and the stored energy levels. For example, if extreme heat is forecasted, the system will conserve energy earlier in the day. Streets with low night activity are dimmed proactively. Stored renewable energy is released strategically during the peak cooling hours. The entire system was designed, modeled, and animated in such a way using computer-aided design and 3D modeling tools, allowing feasibility to be re-evaluated before physical deployment.
This project directly contributes to SDG 7, Affordable and Clean Energy, and SDG 11, Sustainable Cities and Communities, and SDG 13, Climate Action. Extreme heat is no longer a future threat. It's a present reality for the cities in the UAE. Resilient cities are not built only by generating more energy, but by using energy intelligently. By redesigning streetlights as smart, renewable, and AI-driven infrastructure nodes, our solution demonstrates how engineering can transform everyday urban systems into powerful tools for climate resilience and sustainability.